So in this session, we're going to be looking at linked lists. And linked lists are data structures, just like arrays, which we've just looked at. And we're going in this video, we're basically going to just look into the linked list to explore and look at how they relate with the arrays as well, and also how they operate. We're going to be looking into more details on that. But before getting to that, we need to understand what a linked list is. So a linked list is a linear data structure in which elements, and we refer to these elements as nodes, are stored in a sequence where each node is going to contain or contains a reference to the next node in the sequence. So we're going to try and visualize this so that it can make a lot of sense. So here, think of these two boxes that we have here as nodes. So we have a node here, and we're going to create another one. So we have three nodes, and these nodes contain two things. Yeah. So I'm going to split them into two like this. And what they're going to contain is they contain data. So each node contains data that it's supposed to carry and a reference to the next node. Yeah. So we can refer to this like this. So let's say I can just switch the color here. So let's say this is the data that is here. So here is where the data goes to. And the second portion of it is where we have a reference. We have a reference to the next node. So something like this. This is what a linked list would look like. So when it comes to the data, it could be numbers. So we could have maybe this is zero, we have one here, and we have two. So let's say that's the data that it has, and these are references. What we're seeing here, this is what we refer to as a simply linked list, but we're going to be looking into more details on that as we proceed. Before we get into all the other details as well, we need to just look at a little bit of a difference between linked lists, and we had also looked at arrays. So the one of the key things that we need to look at when it comes to arrays and linked list is memory allocation. Yeah. When it comes to arrays, the arrays have a fixed size. I think we've already addressed that. So arrays have a fixed size. But so when it this how this occurs basically is when you want to store elements in an array, you have to know beforehand the size of that array or the number of elements you're going to store so that you can basically create an array of that specific size. But when you talk of a linked list, so I'm going to write linked lists here. When you talk of linked lists, they do not have a fixed size. They have a dynamic size. Now, what you mean by this is that when it comes to memory allocation, it is sort of non-contiguous, and each node is created dynamically, and it can spread across memory, linked together by pointers. So as we've seen here, we have each individual node. Say this is the first node, second node, and on, and they have pointers. So when it comes to a linked list, if I want to add another element into a linked list, all I need to do is just create another node. So I can go ahead and create another node like this, and also this other node is going to contain, of course, a pointer to the next one like this. So you can always add more elements into that. That's why we refer to it as dynamic. But arrays, on the other hand, are fixed because you need to know the size beforehand. Now, another difference between the two comes to insertion and deletion. Basically, when you're dealing with arrays, there's a certain sort of expensive operations that happen. So when you talk of insertion or deletion, an element is going to basically shift the sort of the order in which those elements are being maintained. Yeah. Also, when you talked about arrays, we saw that when you're dealing with an array, once you've created an array and you want to add another element into the array, basically you need to that means you're increasing the size of the array. And since they have a fixed size, you have to go ahead and create a new array that is going to be of the new size that you want. And that's some sort of, it's sort of an expensive. But when you talk of linked list, the operations are a bit more efficient since you can easily insert or delete elements by simply updating the node references and pointers. So we've seen, I'm going to use a different, so we've seen these are the nodes here. Not nodes rather, but these are the pointers, yeah. So as we're going to see in more details, when you want to get rid of an element or delete an element in a linked list, so let's say you want to get rid of this element, this node here, basically, you just need to replace the pointer. So you just replace the pointer instead of it pointing here, you just switch it for it to point to this next element. Yeah, and if you want to add a new, let's say we want to add a new element here, right here, between this node and this one, all you need to do is create the new element, of course, the new node, and switch the pointer. So this pointer will point here, and this one, its pointer is going to point to this other node that we see here. There's also in terms of access. So when you want to access elements from in an array, from an array, we saw when it comes to size. Again, we're going to be looking into more details on this when you look at big O. But when you want to access elements in an array, you're going to use, it's going to be in constant time, which is O of one. But when you're dealing with linked list, it takes linear time. So the reason it takes linear time is because you need to traverse the list from the head to the desired node. So this one is going to take linear time, which is of, and basically all it means, it depends on n, where n is going to be the element that you're looking for. So, or the size of that list. When you talk about linked list, the first element we refer to it as the head, and the last element we refer to it as the tail. Yeah. Then you have all the other elements in between. So at any point you refer to as the head, refer to the first element in a linked list. Now that we've looked at linked list, what we've seen is that, as I mentioned earlier, what we have here, this is what we refer to as singly. We refer to it as a singly linked list. This is what it looks like. And there are various types of linked list. When you talk of singly linked list, basically its node has two parts. It contains the data and a pointer to the next node. Yeah, it's simple and a bit lightweight as well. And when you want to traverse through such a linked list, you just do it one way, so forward, because it's only pointing. The pointers are pointing forward. Yeah, and that's basically it. I think, since we've already used it as an example a few more times, I'm going to leave it at that. So the other type of a linked list is what we refer to as a doubly linked list. Yeah. Let me just use LL again. I have a really beautiful handwriting, so let's go on with it. So when you talk of a doubly linked list, in a doubly linked list, you have a node. So we're going to, of course, you need a node. We're going to create our node here. And now, something interesting about a doubly linked list, or the difference between it and the singly, is that each node is going to contain three parts, or has three parts. It contains a pointer. So let's split this three times. We're going to have this, the first, like this. Yeah. So it contains three parts. Data. So let's say we have the data that node is carrying here, and it contains a pointer to the next node and a pointer to the previous node. So here we have a pointer to the previous node, and here we have a pointer to the next node. That is basically what we refer to as I mean a linked list. What we refer to as doubly linked list looks like. So you're going to have, of course, you have another node here, and still the same. So this node also contains data here, a pointer to the next node, and this is a pointer to the previous node, like that. And this continues and continues. So if you want to visualize, so you're going to have your data here, again a pointer to the next node and a pointer to the previous node. So you can just stack this as our head, and this should be the tail, and you can continue expanding it as you proceed. So one of the advantages of this, which is an advantage that we didn't have with a singly linked list, is that when it comes to traversing, in a single list you can only traverse forward, but in a doubly linked list you can traverse in both directions. So you can traverse forward and you can traverse backwards because of the pointers. It has a next pointer and a previous pointer. So this is what we refer to as a previous pointer, and this pointing forward is the next pointer. Yeah, now the limitations that this might have is it's going to require an extra memory, of course, to store the previous node pointer. Yeah, because in the previous one, the only thing that we're storing the next pointer, but here we have an extra pointer that we need to store. But that is basically what a doubly linked list is and how it looks like. Now we do have another one, which is a circular linked list. So circular, as the word mentions, rather as the name suggests, it's circular. Yeah. So for a circular linked list, it has a similar structure to what you've seen from the singly linked list and the doubly linked list. But the difference here is that now the last node points back to the first node. To visualize this as well, let's go ahead and create this. So we're going to have, these are two nodes. Let's make them three and just move this a bit like this. So here, again, also let's represent it as the way we are representing our doubly linked list. So this is what we have. Again, we have the data here. So this is the data. There's all the data comes here. Then we have the pointers. So there's this next pointer. We have a previous pointer. This one also has a previous pointer. We have a next pointer there and a previous pointer. And this also has a next pointer. Now, this is what this means. For a circular linked list, the last node points back to the first node. So its next node, again, let's take, this is the tail and this is the head here. So this node points back, its next node points back to the head. So hence the circular that we're talking about. So basically how you represent this basically here is that the next pointer for the tail or the next pointer points to the head. Yeah. So that is basically what we refer to as a circular linked list. Some of the advantages is when it's useful for applications. So things like buffering, especially these are some things that are a bit more ahead. Things like the round robin scheduling, which we're going to look at later on. That is where you can apply something like this. The limitation of this, of course, is traversal can't continue indefinitely if you're not careful to stop it in the right condition, since it is circular. So, like here, this one was not circular. So, if you are traversing, at some point it's going to stop. But this one is going to continue indefinitely, since it is circular basically here. Yeah, so basically up to this point, we have covered the key differences between arrays and linked lists. We've looked at some major differences between arrays and linked lists, from the size, where arrays have a fixed size, linked lists have a dynamic size. We've also looked at when it comes to uh, the time it takes to carry out operations in arrays. If you want to do insertion or something like accessing an element, it's going to take O of 1, which is constant time. But for a linked list, it's going to take O of n, which is linear basically. Then we've also looked at now the differences between a singly linked list, a doubly linked list, and circular linked list. Yeah. So in the next video, we're going to look a bit more into these data structures. But thank you for sticking up to this time. See you on the next one.